Welcome to this explainer. I am absolutely thrilled to have you here today. Think for a second about the kind of invisible magic that makes our modern world tick. I'm talking about the unseen spatial awareness that lets self-driving cars weave through traffic, or just basic robotics that know not to slam into a wall. At the very core of that tech is a fundamental concept that we're going to master today. We are going to completely demystify exactly how the Arduino UNO R4 works when it's paired up with the HC-SR04 Ultrasonic sensor. So, if you're looking to build your own highly responsive, distance-aware hardware projects, well, you're in the exact right place. We're going to break down the science, the hardware, and the code, step by step, so you can start engineering your own spatial systems. Let's get into it.
Let's take a quick look at our roadmap, detailing exactly how we'll build this whole thing, from basic physics up to an advanced hardware implementation. We'll start with the operating principle, then move into hardware preparation, walk through the exact wiring, conquer signal processing, build an advanced alert system, and finally wrap it all up with our conclusion.
All right, Part 1. Operating Principle. Understanding signal transmission time. Before we even think about touching a wire or writing a line of code, we really need to understand the theoretical foundation of how this technology actually functions. To really get this, it's kind of like a bat using echolocation in the wild. The sensor operates strictly by utilizing what we call signal transmission time. Basically, it sends a high-frequency sound wave outward into the environment, and then it just waits. Here's the crazy part. The sensor doesn't actually measure distance at all. Nope, it effectively measures a stopwatch. It tracks the precise duration it takes for the echo to bounce off an object and return to the module. It's a strictly time-based measurement protocol. And from that raw stopwatch data, well, we're the ones who do the math to figure out the actual physical space.
Okay, moving right along to Part 2, hardware preparation, exploring the sensor components. Now that we've got the underlying physics down, let's transition to the physical hardware preparation required for our Arduino UNO R4 setup. When you look at the physical sensor, you're going to notice these two main cylindrical components sitting right on the front. At first glance, they look like a pair of identical robotic eyes, right? But in reality, one is a shouting mouth and the other is a listening ear. One side is the transmitter, and its sole responsibility is sending that high-frequency sound wave outward. Its dedicated job is literally to yell into the void. Versus the other side, the receiver, whose only job is to quietly listen for that returning echo. It's this perfectly divided sender and listener pair, heavily optimizing the hardware so those outgoing bursts don't interfere with the incredibly subtle incoming echoes.
To actually bring those two distinct components to life, we need 4 fundamental connections. Rather than just a random jumble of wires, we handle power first and then communication. So for power, the VCC pin takes a steady 5-volt input directly from your board just to wake the sensor up, while the GND pin serves as your ground, connecting to 0 volts to complete the circuit. With power established, we move over to the 2 data lines. The trig, or trigger pin, receives your control signals from the Arduino to initiate that sound wave burst. And finally, the echo pin outputs the critical return signals back to the Arduino, reporting exactly how long that sound wave took to bounce back.
Awesome. Part 3. Wiring. Connecting to the Arduino UNO R4. Let's head over to the workbench and see how this builds into the actual physical wiring phase. Wiring is really where these projects truly succeed or fail. It's absolutely crucial to make these connections in the right sequence, mostly to protect your board and ensure accurate data routing. So you'll want to connect the VCC pin securely to the 5V output on your Arduino UNO R4. Next, wire the GND pin directly to the 0V ground pin. With the electrical foundation safe and solid, go ahead and route your communication lines by connecting your trig pin to digital pin 9 and your echo pin to digital pin 8. By working methodically through this, power first, data second, you guarantee that the electrical logic is 100% ready to function the second you upload your code.
Which brings us to Part 4, signal processing, code, logic, and data filtration. We have our theory, and our hardware is successfully wired up. Now we transition into the signal processing phase, which is where the physical hardware directly meets our software.
So to kick off the measurement cycle in our code, we first have to generate a highly precise 10 microsecond trigger pulse on the trig pin. Just pause and appreciate the sheer scale of a 10 microsecond pulse for a second. It is an unfathomably fast fraction of the blink of an eye. Yet that tiny, rapid electrical burst is exactly what commands the transmitter to fire its ultrasonic wave. Instantly after that burst, our code switches focus to measure the logic level feedback duration from the echo pin. We're effectively commanding the Arduino's incredibly fast internal clock to count the exact number of microseconds that the echo pin remains in a high state while it waits for that sound to return.
And now, here is where the magic number comes in, 0.017. This is the secret sauce. Once our code has counted the duration of the trip in microseconds, it applies this exact mathematical constant. You might be wondering why this specific number. Well, the speed of sound through the air is roughly 0.034 centimeters per microsecond. But remember our bat echolocation analogy? Our sound wave has to travel all the way out to the obstacle, bounce off, and then travel all the way back. We're capturing a round trip, so we absolutely must divide that speed of sound in half, which perfectly gives us 0.017. Multiplying our timer by this constant brilliantly converts a raw microsecond duration into a highly usable distance in centimeters.
However, we've got to address a very real critical problem that plagues hardware engineering. Raw sensor data inherently contains noise, which causes incorrect distance readings. If you've ever built a little robot that was driving perfectly and then suddenly jerked sideways for literally no apparent reason, yeah, you have experienced this exact phenomenon. Sound waves are chaotic. They bounce off weird irregular angles, they get absorbed by soft materials, or they might even encounter acoustic interference from the room itself. If our code just blindly trusts every single raw mathematical measurement, our project is inevitably going to suffer from erratic behavior, false triggers, and ghost readings. Nobody wants that.
To fix this chaos, we implement a highly precise, systematic solution, a moving average filtration algorithm. Think of this as putting a rigorous quality control filter on our data. Instead of trusting a single, potentially noisy reading, we command the Arduino to quickly take a batch of 20 separate measurement samples and store them in an array. Then, we mathematically sort that entire array in ascending order. Next, and this is key, we strictly drop the 5 highest values and the 5 lowest values. We toss out these extremes to instantly eliminate wild outliers. You know, like a sudden rogue echo bouncing off a table leg or a missed ping. Finally, we calculate the true average using only the remaining 10 middle reliable samples. This routine results in incredibly stable, rock-solid distance data that your system can actually trust.
All right, Part 5, Advanced Alert System, Practical Application Integration. We've captured the data, mathematically converted it, and cleanly filtered it. Let's move right into our practical application integration.
Finally, part 6, conclusion, summary, and next steps. Let's pull all of these engineered pieces together and take a look at the big picture.
We've seen how building a robust spatial system is really a layered process. It all starts with the simple, underlying physics of signal transmission time. But to tap into that physics on your workbench, you absolutely require a rock-solid electrical foundation through a precise 4-pin wiring setup. Raw hardware just isn't quite enough on its own, right? You must bridge the gap with software by implementing moving average filtration to guarantee code reliability and filter out that inevitable acoustic chaos we talked about. When you combine clean, filtered data with strict conditional logic, you unlock the ability to build incredibly robust applications. I'm talking anything ranging from a simple desktop proximity alert all the way to highly complex robotic collision avoidance systems.
We've journeyed from the fundamentals of sound wave physics through meticulous hardware wiring all the way into advanced software data filtration. You now have the exact tools to make your microcontrollers fully aware of their surroundings. So, I want to leave you with this final thought to really spark your engineering curiosity. What real-world automated system will you build using this precise, moving average filtration logic? Thank you so much for exploring this explainer with me today. Keep building and stay curious.